Morning. So I had a really interesting revision session with one of my GCSE students today, and she was asking me about moles. And she left laughing about how relatively straightforward moles are compared to what she had expected. So I was exactly the same. I could not get my head around moles whenever I was in school, even whenever I was in university. I was still took a lot of practice getting my head around it. And it was one of those things, as soon as it clicked, it made perfect sense. And actually, moles can be really difficult to explain sometimes, but actually it can be really straightforward as well. And all you need to remember for moles is that it's just the amount of a substance. That's all it is. It's just a measure of how many particles or how many things of that substance there are. And we use things like this all the time. So when it comes to talking about a pair, we say a pair is two things: a pair of socks, a pair of bananas, whatever. The same for a dozen. So a dozen is 12 things, whether it's a dozen donuts, a dozen elephants, a dozen water bottles. It doesn't matter what those things are, so long as we're talking about just 12 of them. And it's exactly the same thing for moles. For moles, it's to do with the amount of either atoms or molecules there are of a substance, okay? And because these things are so small, we need actually a really big number to make it sensible, okay? So instead of being 2 or 12, the number is actually 10 to the power, or 6 by 10 to the power of 23, okay? And that number is called Avogadro's constant. So there's a whole pile of science behind why this particular number and how it's been developed. You don't need to know any of that. Just remember the actual number is 6 by 10 to the power of 23 particles. Whether those particles are atoms or molecules, it doesn't matter, okay? So long as you're talking about the same number of them. And this 6 with 23 zeros underneath here is showing you the size of that number, okay? So that's why we break it down using 6 by 10 to the 23. But also it's why we, instead of having to say 6 by 10 to the 23 molecules each time, it's easier to say a mole of that particular substance, a mole of those molecules, a mole of that atom, okay? Because when I say 1 mole of carbon, you know I'm talking about 6 by 10 to the 23 carbon atoms. If I say a mole of water, you know that I'm talking about 6 by 10 to the 23 molecules of water. And depending on what those particular particles are, what the molecules are, what the atoms are, they're going to weigh different amounts, or they're going to have a different mass, to be more precise. So just the same as a dozen feathers is going to weigh less or have a smaller mass than a dozen eggs, having a mole of carbon is going to have a smaller mass than a mole of water, or H2O. And it's because the actual mass of those things differs, okay? So it really doesn't matter what it is we're actually talking about, okay? So you can see here, 1 mole of elephants is 6 by 10 to the 23 elephants. 1 mole of carbon is 6 by 10 to the 23 carbon atoms. 1 mole of water is 6 by 10 to the 23 water molecules. So it really doesn't matter what the actual molecule is, so long as we're talking about the amount of that molecule. So 6 by 10 to the 23 is Avogadro's constant, and that is 1 mole. If we talked about half a mole of elephants, we would be saying 3 by 10 to the power of 23 elephants, because it's half of that number. If it's 2 moles of elephants, it is going to be 6 times 2, which is 12 by 10 to the power of 23 elephants, okay? The same thing for carbon and water. So in your notes and in your questions, you'll see 2 moles of this, or half a mole of that, or 0.05 of a mole, okay? And all that is just saying the relative amounts of that group of particles. Is it the full group? Is it half of that group? Is it 2 of those groups, okay? So if you are looking at the actual mass then, okay, we talk about mole being the number of substances. So the number of particles, the number of molecules, the number of atoms, but they all have their own mass as well. So a mole of something will have a mass too, okay? We can weigh out 1 mole of the substance. And depending on that substance, it's going to have a different mass. Just the same as different elements and atoms in the periodic table have got different atomic masses, different molecules will have different atomic masses. So therefore, their moles will have different masses as well. So in the example here, I've got magnesium. Okay, so if you look at your periodic table, you'll see magnesium with a 12 and a 24 beside it. Okay, and 24 is its atomic mass. So we can say the atomic mass of magnesium is 24. So magnesium's molar mass is also going to be 24. Okay, so it's just the numerical equivalent. We say it is 24 grams. So if I wanted to weigh out 1 mole of magnesium atoms, I would weigh out 24 grams of magnesium. The same thing for carbon. So when you look at your periodic table, carbon's atomic mass is 12. So we would say then that carbon's molar mass is just the gram equivalent of that, 12 grams. So 1 mole of carbon is going to weigh 12 grams. Half a mole of carbon is going to weigh 6 grams. And we know that in those 6 grams of carbon, we have got 3 by 10 to the power of 23 molecules there, okay? Or atoms in the case of carbon. So when it comes to water, you actually need to work out not just the mass of the individual elements or atoms in there, but you need to work out the molecular mass, okay? So this relative molecular mass is what we need to work out. And by doing that, you need to know the formula, the molecular formula for water. So we all know it's H2O. So that means the atomic mass of hydrogen is 1, but because it's H2, we need 2 of them, and that leaves us with 2 then. Oxygen, the atomic mass of oxygen is 16. We only need 1 of them, so it just stays at 16. 2 plus 16 is 18, so then we would say 18 is the relative molecular mass of water. So 1 mole of water, 1 mole of H2O equals 18 grams. Very often you'll be asked how many moles are there in a substance. So if someone said, here's 18 grams of water, how many moles are there? You can say, well, okay, that is 1 mole because 1 mole weighs 18 grams. If it was 24 grams or 6 liters or an entire swimming pool of water, how many moles are in that? So instead of counting out each individual molecule, which really is pretty much impossible, instead we can work it out using this equation, okay? So the equation is the amount of moles in a substance equals the mass of that substance, how much of it you actually have, whether it's 1 liter, 10 liters, or 18 grams, divided by its relative molecular mass, okay? Or the size of each individual molecule making up that substance, okay? And the triangles are brilliant. The triangle that it fits into is this shape here, okay? So mass is on the top, then you've got relative molecular mass down here and moles down here. And I'm sure by now you're all well used to it from physics. You can just shuffle this equation around, okay, or shuffle this triangle around. But what we're going to do is focus on figuring out how many moles we have. So to do that, it's mass divided by the relative molecular mass. So let's try that. Looking at the number of moles in 4.9 grams of sulfuric acid. So we have 4.9 grams of sulfuric acid, and we want to figure out how many moles of that we have. Do we have 1 whole mole of it? Do we have more or less? Okay. So to do that, we have to know our equation. Our equation is moles equals mass in grams divided by the relative molecular mass. So mass in grams is going to be 4.9 grams, because we know that from our question. The relative molecular mass is going to be the relative molecular mass of sulfuric acid. And it's a bigger molecule than water, so it's going to take a little bit more working out. It's H2SO4. Okay, so H2 means that we have got hydrogen and its atomic mass is 1, but we need 2 of them, so that total is 2. For sulfur, okay, we only need 1 sulfur. Its atomic mass is 32. We only need 1, so it ends up at 32 again. Oxygen, its atomic mass is 16, but we need 4 of them because it's O4. Okay, so 16 multiplied by 4 is 64, and we just add all those up again and we get 98. So our relative molecular mass is 98. So we'll just plug that then into our equation. 4.9 divided by 98. And if you have your calculator with you, please don't use your phones for calculators if possible. You need to use an actual calculator in your exam, so get used to using one of them. It gives us 0.05. So we can say the number of moles here is going to be 0.05 moles. And we write it very often with that little abbreviation, MOL. So that's your answer. Okay, so we can say that actually we don't have 1 full mole of that. Okay, we don't have 6 by 10 to the power of 23 molecules of sulfuric acid. Actually, we only have 5% of that. So that's why we would want to do that. And it's really important if you're working in a lab and having to measure out quantities and make up things, okay? If you remember from your respiration equations, for example, 1 mole of glucose, okay, or 1 molecule of glucose needs 6 molecules of oxygen to fully complete that respiration equation. So if you were going to be weighing out a certain amount of glucose, you need to know in comparison how much oxygen you need, okay? And it's really useful then for working out things whenever you're doing pharmaceuticals, biomedical science, anything to do with medicine and chemicals and things like that as well. So you can change the equation around to solve problems in different ways, okay? Instead of saying how many moles are in this, we can say I need 0.5 moles of that. How much is that I need, okay? So 0.5 moles of calcium hydroxide, what mass is that? How much of that do I need to weigh out? So let's work that one out as well. From our triangle, we can see that mass is always on the top, moles and relative molecular mass are on the bottom. So we can say mass then equals moles multiplied by the relative molecular mass. We need 0.5 moles, okay, so our moles is pretty straightforward. We can just do 0.5 times the molecular mass of calcium hydroxide. So it's CaOH2. We need to work out what the relative molecular mass of this is. Okay, well, let's do that then. Calcium, its atomic mass is going to be 40. We only need 1 of them. So we end up with 40. Whenever you have OH in a bracket with a number beside it, that means both of those atoms or elements need to be increased by that number. Okay, so here we have OH in brackets with a 2 beside it, which means we need 2 oxygens and 2 hydrogens. Okay, so oxygen is 16 multiplied by 2. And hydrogen is going to be 1 multiplied by 2, okay? 16 multiplied by 2 is 32. 1 multiplied by 2 is 2. And you can see then we get 74, okay? So the relative molecular mass of calcium hydroxide is 74. So it's very simple. We just add it all in. 0.5 multiplied by 74 is going to be 37. Just double checking myself. 37 grams. So if you're in a lab and someone says to you, you need 0.5 moles of calcium hydroxide, no problem, 37 grams weighed out, off we go. And that's really all it is, okay? It's very easy to get really, really kind of complicated and be overwhelmed by moles because of the way that you have to think about it. But if you just remember, you're just talking about how many molecules or how many atoms of that substance, okay? How many particles of that substance. Each of those particles will have a different mass. So the mass of moles will change, but the number of particles within 1 mole will always be the same no matter what the particle is. So 1 mole will always be 6 by 10 to the power of 23 particles. The mass of that mole will vary depending on the mass of the particle, but you'll still always have the same number of particles there. Half a mole is half the number of particles, 2 moles is double the number of particles. And it's just a really straightforward way for scientists and chemists to be able to talk about amounts of substances whenever the actual molecular mass or atomic mass is so small that it doesn't make sense to talk about it in terms of that, okay? You just group it into a bigger number so that it makes more sense. We say a pound coin instead of 100 pennies. We say a 10-pound note instead of 1,000 pennies. Okay, we do this all the time. The only difference is, in this case, instead of talking about something that you use every day, you're talking about molecules and atoms. But the more you do these equations, the more you practice at it, the more sense it will make. And I promise you, the much more straightforward it will be. So good luck. Good luck for your exams.